cx plus dy was there here. Okay, so for this one we need to convert this in terms of the y we need to express here. We need to find out the value for the y. So what shall we do is we can express the x in terms of the in any of the equation we can substitute x in terms of the other random variables. Let us express here and let us substitute for the x in this equation here. Okay, so from this one, so we got ax is equal to, so send by that side, so u minus by. Okay, so this implies that x is equal to u minus by divided by a will get here. Okay, so solve for ax here. Ax is equal to send by this side, so u minus by divided by a will get here. So that is x is equal to, let us substitute x here. So v is equal to, okay, c into x is nothing but, so u minus by divided by a plus dy. Okay, so let us take the LCM for this one. Let us take the LCM for this one. So it has become, so c into u, let us multiply in the meantime. So bc into y plus d into a into y. So divided by a will get here. So cross multiply a. So a into v is equal to c into u minus, okay, so plus, let us take y common. So it has become ad minus bc will get here. Ad minus bc. Let us solve for y. So if you send this side, so it has become av minus u into c divided by ad minus bc will get here. Ad minus bc. So got it now. So we got this expression, and for the x we got in the previous class we had done for that one. The x we got as the inverse transform variable, which is nothing but, so ud plus by divided by ad minus bc we got here. Ad minus bc. Okay, so done. So we have done the inverse transformation of the random variables we had done here. Okay, so now what shall we do? Okay, so just some are in lobby, so I just admit them. Okay. Okay, fine. Okay, fine. So now we have converted, we have done the inverse transformation. So where we got x and y we got here. So x is equal to this one and y is equal to the, okay, so y is equal to this quantity we got here. Now let us substitute a is equal to, so we are going to substituting a is equal to cos theta and b is equal to minus sin theta here. So this is, we are converting the these random variables, the values constant we are converting as that. So trigonometric functions we are converting here, and we are going to find out the angle of angle between the two random variables you are going to find out here. Angle between the two random variables you are going to find out here. Let us substitute c is equal to sin theta and d is equal to cos theta. Let us do substitute here. Okay, c is equal to sin theta and d is equal to cos theta. We are going to do substitute here. So in this random variable y and x here. So let us substitute here in place of x. So u into d is nothing but it is a cos theta. Okay, so plus in place of b we have sin theta here. So minus sin theta into v divided by a into d. So it is cos square theta. Okay, minus sin square theta, minus sin square theta will get here. Okay, so cos square theta minus into minus will become plus will get here. So cos square theta minus sin square theta will become 1. So x we got as u into cos theta minus v into sin theta will get here. V into sin theta will get here. Okay. X we got this one. So u into cos theta minus v into sin theta. So this is correct now. Plus b into v. It's correct, right? B into v. Sorry, here it's minus come here. Minus should come here. Minus should come here. Okay. Minus should come. So this is the minus into minus will become plus here. So this is become u into cos theta plus v into sin theta will get. So similarly, the value of y is equal to. So this is minus here. A into v. So a is nothing but it's a cos theta. A is nothing but cos theta. Okay. Okay, so a is nothing but cos theta, and v we are going to keep like that only. V minus, okay, u into c is nothing but sin theta. C is nothing but sin theta. Okay, so divided by, so in the denominator we have same thing. So it is cos square theta plus sin square theta will get here. Sin square theta will get here. So this has become minus u into sin theta plus v into cos theta will get here. So that is the random variable x and y will get here. So for the random variable x and y, so you're going to substitute here. So here already we are done for the AD into AD minus BC. So this one will get here. Okay. So done, right? Okay. Okay, fine. So now let us find out the mean and variance of this one here. Let us find out the mean and variance of this one. So we have, I'm going to rewrite here. So x is equal to, we have x is equal to, so here we have x is equal to u cos theta plus v sin theta we have here. So u cos theta plus v sin theta and y is equal to, so we have y is equal to minus sin theta into u, okay, or minus u into sin theta plus v into cos theta. V into cos theta we have here. Now let us find out the mean and variance of this one here. Let us find out the mean and variance of this one. So we can take the mean and the mean of the random variable x and y is given by the mean of the random variable x and y is given by the mean of the random variable x and y is given by. Okay, so let us find out the mean here. The mean of this one is nothing but it's the expected value of x here. The expected value of x is nothing but it will become mu x here, and u we know that already the mean of this one is a new year. Okay, so we can write this one as nu into u plus sin theta. It's a constant here. The expectation of constant is nothing but constant only, it will remain here, so it will become nu into v. And similarly the expectation of y, so this will become nu into y, which will become equal to the, so minus sin theta into nu u plus so cos theta into nu v will get here. Cos theta into nu v. Okay, cos theta into nu v will get here. So done. Done, right? Okay, so fine. So now let us find out the, so any doubts? Okay, so similarly let us find out the variance of this one. So in order to find the variance of this one, I'm going to recall the concept of nu u here, how we find the variance of this one here. So we have nu is nothing but a square into sigma x square plus b square into sigma y square plus 2ab into covariance of xy. Okay, so we got like this here. Okay, so similar way what you are going to do is we are going to find out the variance of this one. So just I'm going to change the variables as per this one. Okay, so you can take the variance of the, so as per this one I'm going to change here. You can take the variance of x and y is given by the variance of x and y is given by the variance of x and y is given by the variance of x and y is given by. So you can take this expression. Okay, so the variance of x and y is given by, so it is nothing but sigma x square. I'm going to change the variable accordingly. Sigma x square into, so a square into sigma u square here. So the first variable is u here plus, okay, so b square into sigma v square here. The second variable is v here plus 2ab into, so covariance of the random variable u and v here. The covariance of the random variable u and v. So we know, okay, sigma x square, we know the value of a here, and we know the value of b, and we know this one. So a is nothing but, so it's a is nothing but it's cos theta, b is nothing but sin theta here. So a is nothing but cos square theta into sigma u square plus minus sin square theta will become sin square theta, okay, into sigma v square minus, okay, so minus will get y because 2 into cos theta into sin theta will get here. So cos theta into sin theta, so minus 2 cos theta into sin theta into covariance of u and v. Covariance of u and v will get here. Okay, done. So similar way we can write the covariance for the random variable y in terms of the transformed random variables. So it is, first I'll write that one. So c square into sigma u square, okay, plus d square into sigma v square plus 2cd. Okay, plus c into d into covariance of u into v. Covariance of u into v. C is nothing but, so we have c is nothing but sin theta, d is nothing but cos theta. Okay, so let us do substitute here. So it is sin square theta into sigma v square, sorry, sigma u square. Okay, and cos square theta into sigma v square plus, okay, so here both are positive, sin and cos both are positive here, so we can say plus 2 sin theta into cos theta into covariance of u and v here, covariance of u and v. Okay, so that one will get here. Done. Okay, so we got the variance of the transformed random variable, that is for the inverse transformation. We got this one here. So sigma y square is equal to, so sin square theta sigma u square, like this here. Okay. So similarly, we'll find out the covariance of the random variable x and y here. Similarly, let us find out the covariance of the random variable x and y. So already we derived in the class here. Okay. So just I'll take that sheet. Okay. I think everyone has taken this one. So everyone has taken this one.
Yes, sir.
Yeah. Okay. Fine. So now we have seen the covariance of u and v. It is given by AC into sigma x square into covariance of xy into AD plus BC into BD into sigma y square here. Okay. So similar way, let us write. So I can take the covariance of x and y. The covariance of x and y is given by, so x and y is given by, so the covariance of this random variable x and y is given by, so I'm going to write the expression in terms of the random variables, in terms of the values. So it is a into c, okay, a into c into sigma u square plus covariance of u into v into AD plus BC plus B into D. So here we have sigma y square, so we can write as sigma v square, we can write here sigma v square. So similar way how we got this one, the same way I have written the expression here based on this concept here. So just I'm interchanging the variables x and y, I interchange with the u and v here. That's it here. So now let us substitute for the A and C. So covariance of A and C. So A is nothing but it is the cos theta and C is nothing but sin theta. So cos theta into sin theta will get here. Okay, so A into C is nothing but cos theta into sin theta, correct now? So A is cos theta, C is sin theta. Okay, so cos theta into sin theta into sigma u square plus covariance of u v. Okay, so into AD plus BC. So AD minus BC is equal to 1. AD minus BC is equal to 1, but AD plus BC is equal to something different here. So let us do substitute here. So AD is nothing but cos theta, D is also cos theta. It will become cos square theta minus sin square theta will get here. Okay, so plus, okay, so plus or minus will come. Okay, minus will come, minus sin theta into cos theta. So this is a BD. So I can write as minus sin theta into cos theta into sigma v square will get here. So this is u and this is sigma v square will get here. Then, so this is the covariance of the random variable u and v. Okay, so here what we can take is, here cos theta sin theta is there, cos theta sin theta is there. We can take this common here and we can rewrite the expression. We can write here. Okay, done. So let us rewrite here. So I'm going to rewrite this one. Okay, so what I'll be writing is, so I'm going to take, okay, so I'm going to take covariance of xy. So this one will be taken as, so covariance of x and y. So let us take cos theta sin theta, let us take common here. So it will become cos theta sin theta. So this is sigma u square minus sigma v square plus, okay, so this terms will come covariance of u v into cos square theta Okay, so into, sorry, minus sine square theta minus sine, okay, so this is over. And this terms will get here. Okay, done. Done, right? Okay, so this is the covariance of the random variable x and y we'll get here. So now already we have seen the concept in the long back in the previous classes we have seen here. Suppose if the random variable x and y are uncorrelated here. So we have seen the concept of uncorrelated random variable. Okay, so here we can have the concept of uncorrelated random variables. Okay, so done. I think everyone has taken this one. Everyone has taken this one, right?
Yes, sir.
Okay, fine. So for the uncorrelated random variable, we have seen that suppose if the random variable x and y are uncorrelated, then the expected value, the joint probability, or
Yes,
the
sir.
co-expected. Yeah, tell me. Okay, so if the random variables A and B are uncorrelated as the occurrence of the one event does not depend on the occurrence of the other event. We are going to call this one as the uncorrelated or the statistical independent. We can call it here. So for that one, the expected value of x and y is equal to the product of the individual means will be there here. So in that case, covariance of x y will become equal to the. So it will become equal to 0 here. Covariance of x and y is equal to 0. Is equal to 0. Now what shall we do is, okay, so we are going to equate that. Suppose if the random variable x and y are uncorrelated, then this covariance will be equal to the 0 we'll get here. So this covariance will be equal to 0. Okay, so you can take here. Okay, so you can take. Suppose if the random variable, suppose if the random variables you can take here, random variables x and y are uncorrelated, then covariance of x and y is equal to 0. Covariance of x and y is equal to 0. So in this case, so this implies that, so 0 is equal to, so cos theta into sin theta into sigma u square minus sigma v square plus covariance of the random variable u and v. So we are not considering the u and v are uncorrelated, but it is depends here. We are going to assume like that only, into cos square theta minus sin square theta will be considering here. This will be equal to 0 in it. Okay. And also, okay, so we equated the covariance is equal to 0. We are equated here. So now we got here. So cos square theta minus sin square theta is it. So the cos square theta minus sin square theta is equal to, we know that this is equal to the 2. Okay, it's a cos 2 theta here. So you can take, we know that. So from the trigonometric formulas, you know, cos square theta minus sin square theta. So this is the thing about cos 2 theta, cos 2 theta. So similarly, we have cos theta, 2 cos theta into sin theta, 2 cos theta into sin theta, sin theta into cos theta. This is the thing, but sin 2 theta here, sin 2 theta. Okay, so what I'm going to do is I'm going to place substitute in place of this one as cos 2 theta. In place of this one, I'm going to substitute as a sin 2 theta. I'm going to substitute here. Okay, so if you're going to substitute, let us, okay, so 0 is equal to, this has become, since 2 is not there, so what can I write is, so I can write as a sin 2 theta divided by 2 I can write here. Okay, sin 2 theta divided by 2 I can write here. Okay, so sin 2 theta divided by 2 I can write. So this will be the sin 2 theta divided by 2 into sigma u square minus sigma v square plus, so this is cos 2 theta into covariance of the random variable u and v, covariance of the random variable u and v. Okay, so let us send this one to the LHS part here, or anyone now you can send to the LHS part. So sin 2 theta divided by 2, so into sigma u square minus sigma v square. So this is equal to the, so I'm sending here, so this will become minus cos 2 theta into covariance of u and v. So let us cross multiply here. I need to express in terms of the tan theta. I need to express here. So let us cross multiply. So if you cross multiply, what will happen is, so cross multiply, what will happen is, okay, if we cross multiply, it will become sin 2 theta divided by cos 2 theta. So this will become equal to the, so minus covariance of the random variable u and v divided by, so 2 will come here, so minus 2 into cross multiply 2 will come, so sigma u square minus sigma v square will get here. Okay, sigma u square minus sigma v square. Done. So here minus is there, so here also you can take minus common here, so this will become equal to the, so 2 into covariance of the random variable u and v, so divided by, if you take minus common here, so sigma v square minus sigma u square. Okay, so then we'll get, okay, sigma u square minus sigma v square. So we know that the sin theta divided by cos theta is nothing but, it's a tan theta, tan to 2 theta it will become here. So this is nothing but 2 into covariance of u unto v divided by, so sigma v square minus sigma u square will get here. Okay, sigma v square minus sigma u square. So this will be helpful in order to find out the angle between the any two random variables. If you want to find out here, so there you can make use of this one here. Okay, so in order to find out the angle between the any two random variables, we can make use of this one here. So where do we need to find out the angle between these two random variables is, suppose assume that we are going to transmit in case of the communication here, in case of the digital communication, we are going to transmit the two symbols by using the two different carrier signals you are going to transmit here. For example, you might have come across the frequency modulation. So there we are going to use a different frequency for the difference data. Okay, so like that, if you are going to transmit the data 1 with one frequency, the data 0 with another frequency, so these two signals are nothing but the we are going to say it's a these two signals should be orthogonal to each other, should be there here. Orthogonal is the thing, but so for example, if you transmit the symbol 1 with the cos theta, and the symbol 2 has to be transmitted with the sin theta, we need to transmit here, so that both will be the orthogonality will be there here. So in such kind of cases where we need to find out the angle between the any two random variables, so there we are going to make use of the, so this angle we need to find out here. So there we can make use here. So when you come to the 6th semester in the digital communication, so we are going to there we are going to find out this concept you are going to make use there here. Okay, so done. So done, right? Any doubt in this one? Yeah. So I think you got the concepts here. So let us see some problems on this one here. So far we have seen what are the concepts you have seen. Just I'll recall the concept here. Okay. So after recalling, just I'll go with the problems. So best in order to remember the formulas, I'm going to recall some few problems, few formulas I will recall here. Okay. So we are done with this one. Yeah. So this is. So done, right? So these are pretty. Okay, fine. So just I'll recall the formulas. What are the formulas we have here? Okay, so just I'll recall the formulas and I'll go back to the actual some problems. Let us see here. Okay, so here. So first we have seen the bivariate random variable. So for that one we have seen the for that one. Okay, so for that one we have seen the cumulative distribution function, which is given by fx of y is equal to probability that x can take the value less than x and intersection of that one here. Okay, so this is the how the CDF has been defined here, the bivariate CDF here. So it is having certain properties. Those properties are nothing but, so fxy of x comma minus infinity is 0, and these are the properties already written in your IA. Okay, so for the bivariate PDF we are written fxy of x comma y. So this is the limit. If you're going to differentiate the CDF, you are going to get the PDF you are going to get here. Okay, so for the PDF we have certain property, that is we can obtain the it is possible to extract the PDF fxy from the joint PDF or the bivariate PDF you can extract here. So that one you're going to call it as so marginal PDFs you're going to call here. So it is having certain property, that is fx of fxy of we can obtain the CDF from the PDF by integrating from minus infinity to the y and minus infinity to the x. So like this we can do it here. And also for the PDF we have one of the property which is called the volume under the bivariate PDF is equal to the 1 is there here. The volume under the bivariate PDF is equal to 1. So we are seeing one concept of how to find the area we are seeing here. And after that we have obtained the marginal CDFs and marginal PDF you obtained here. So this is a bit important here. We are going to find out this one. Suppose if you want to find out the mean and variance of these random variables, we need to convert the joint PDF into the marginal PDFs. We need to convert like this here by using these formulas. And by using this one, we are going to find out the mean and the variance. Let us look in the problem here. Okay, so this is the marginal PDFs. So afterwards, you have seen the independence. Okay, so how if the random variables are the independent, their joint PDF or the bivariate PDF is equal to the product of the individual PDFs will be there here. Okay, so we are going to verify this property also. And the multivariate density function we have seen, and expectations we have seen. So the expectation of the random variable we are going to call it as a correlation. We are going to call here. So we're going to use this one in order to find out the expectation of the correlation between the random variable x and y. Okay, so afterwards, this is for the discrete random variable. So for the covariance, we use the formula. The covariance is nothing but, so it's the expected value of the correlation and difference if the and minus the product of their means here. Okay, and uncorrelated, for the uncorrelated random variables, we have covariance is equal to 0 will be there here. And for the orthogonality, the covariance will be equal to the minus nu x into nu y will be there here. Okay, so this is for the independent, and this is the correlation coefficient you're going to call here. That is rho x comma y. Rho xy is equal to the covariance divided by the product of their standard deviations will be there here. So right, and these are the bivariate transformations we are did in this class here. Okay, so these are the concepts you are seeing here. So let us look into the formula, or let us look into the problem by making use of these formulas. Let us use here. Okay, so done. Take one problem. So it is a exercise, that is it's a solved problem in the your textbook. Okay, so take the bivariate PDF of. So take the problem here. The bivariate PDF of the random variables of the random variable x and y is shown below. The bivariate PDF of the random variable x and y is shown below. Okay, is shown below. Find the following. Find the following. First one is marginal PDFs. Marginal PDFs. Okay, so second one is mean. Next, correlation. And the next one is so let us find out that one, mean correlation. So let us see that one. So mean correlation. So let us find out these things here. So it is given the bivariate PDF. It has been given in terms of the random variable x and y. So this is the y-axis, and this is the random variable x here, and this is a 0, and it is given. So fxy, it's a bivariate PDF here, or we can call it as a joint PDF. So this is equal to 1 from 0 is less than x comma y. So it will x and y both will take the same interval it will take here. Okay, so both x and y will take the same intervals it will take here. So if it is given 0 is less than x comma y is less than y, don't assume that x is less than 0, y is less than 1. We can don't assume that one here. Okay, so don't assume as 0 is less than x and y is less than y, you don't assume, but this is a joint random variables. So it means that both x and y will take the value between the 0 and 1 it will take here, 0 and 1 here. Okay, so usually you'll get confused here, and 0 otherwise here. So 0 otherwise. Okay, it will be 0 otherwise. So done. So it means that, so for x is x and y for less than 1, it will be having the value 1 will be there. So elsewhere it will be equal to 0. So let us mark x is equal to 1, and let us mark y is equal to, so 1 here. So the intersection of that one will become equal to like this here. So it is 1 here. Okay, so for x is less than 0. Okay, so this is so from 0 to 1 it is having the value 1 will be there. So from 0 to 1 it will be having the value 1 will be there. So that one you're going to call it as a, so this is the y-axis, and this is called as a fxy of x comma y, we can call it here, fxy of x comma y. So this is 0 comma 1. So in the 1 comma 0. So the value of x-axis is 1 and the y-axis is 0, and at this point it is the value of y-axis is 1 and x-axis is 0. So here both the values of x and y-axis are 1 1, and here both the values of x and y-axis are 0 0 here. Okay, so we can represent the coordinates, the points we can represent like this here. So this is 1 comma 0. Okay, and this is 1 comma 1, and this is 0 comma 1. like this here. Okay, so except this one. Okay, so except this quantity, for example, if I'm going to redraw this one like this, so this is okay, so 1 comma 0, this is 0 comma 0, and this is the product of x and y. So based on the product of x and y, it will be defined here. So this is 1 comma 1, 1 comma 1, this is 0 comma 1. Okay, so this is fxy of x comma y. So except this area, so remaining part will be equal to 0 will be there. For example, if I'm going to drag the line, so this part will be equal to 0 will be there, and even this portion, whatever the portion will be there, so this portion will be equal to the 0 will be there. Only the PDF will be defined within this range. It will be defined here. The PDF will be defined within this range. It is going to be defined here. So like this, we can do analysis here. So some more properties we can verify for this one, like a CDF we can verify. So let us so just skip that property time being. Okay, so we are going to find out the marginal PDFs, mean and the correlation. Let us find out that one here. Okay, so then we'll find out the mean marginal PDFs. So let us find out first here. Later we can go for finding the PDFs here. So I've seen just recall you've taken these figures. So this is the expression will be given. Based on that one, you need to draw it here and you need to express like this here. Okay, so if you draw this one, that is sufficient here. So the marginal PDFs is given by, so you can take first one is marginal PDFs. So you can take the marginal PDFs are given by, the marginal PDFs are given by. So it is, first let us find out the PDF fx of x. So marginal PDFs is the thing, but suppose if you are going to obtain the single PDF from the bivariate PDF or the joint PDF you are going to call here. So then we are going to call it as a marginal PDFs you are going to call here. Marginal PDF. Okay, marginal PDFs you are going to call. So how it will be find is, so from 0 to infinity. So this is the general formula I'm going to write here. So minus infinity plus infinity fxy of x comma y, and you're going to integrate this one with respect to the random variable dy here. So in order to get fx of x, we need to integrate with respect to random variable y. In order to get fy of y, we need to integrate with respect to the random variable x. We need to integrate here. So let us substitute here. So fx of x. So since we know that the fxy of x comma y is defined between 0 to 1 only, so the limits will change accordingly. So 0 to 1. The value of this one is equal to the 1 year, and we are going to be integrated with respect to the random variable dy. So you know the integration of 1 is nothing but y. The limit is from 0 to 1 year, so it will become 1 minus 0. Okay, so 1 minus 0, so this will become 1 year. Okay, the limit is 0 is less than x is less than 1 year. Okay, so just I'm going to rewrite here. Fx of x will be equal to the 1. So why this is because it has been defined from this limit only. So 0 is less than x is less than 1. Okay, so this is okay, and 0 otherwise. 0 otherwise. So similarly, we can find out the other marginal PDFs. The fy of y we can find out here. So that is integral from, I'm going to write the generalized formula first here. Okay, so fxy of x comma y, we are going to integrate with respect to the dx. We are going to integrate here. In order to get a y, I need to integrate with respect to dx here. So here the limit is from 0 to 1. Why? Because fxy of x comma y is defined between 0 to 1 only. So it is 1 into dx. So the integration of 1 is nothing but x here. The limit is from 0 to 1. Substitute the limit, it will become 1 here. So similar way, let us define here fy of y is equal to, so it is 1 from 0 is less than y is less than 1, and 0 otherwise here. 0 otherwise. Okay, so like this we can find out the this one, the marginal PDFs from the joint PDFs or the bivariate PDF here. Done. Okay, so now what shall we do is I will verify some properties here. So here we have okay, so we obtained the fx of x and fy of y we obtained here. Okay, so let us take the product of this one here. So we have fx of x. The fx of x is nothing but it is 1 from 0 to x here, and fy of y is nothing but it is 1 from 0 to y. So what I'll do is you can take consider. So we'll consider the product of fx of x into fy of y. So for the x here it is 1 from 0 to 1 year, and for fy of y it is 1 from 0 to 1 year. So we can say it is equal to 1 from 0 is less than x is less than 1. Okay, and 0 is less than y is less than 1. So we can combine these two and we can write like this as 0 is less than x comma y is less than 1 and 0 otherwise here, and 0 otherwise we can write here, 0 otherwise we can write here. Done. So this is the product of this one you are going to take here, product of this one. Okay, so the product of the two PDFs you are going to take here, the product of the two PDFs. Okay. Okay, so all of you taken, right? Okay, so done. Okay, now what shall we do? We have seen one of the property we have seen for the uncorrelated random variables. So we have seen the concept of the uncorrelated random variables. So for the uncorrelated random variables of the, okay, so this one here already we have seen the product of the PDFs will be equal to the, okay, so the giant PDF will be equal to the product of the individual PDFs will be there. So that is for the uncorrelated random variables we have seen here. So just yeah, uncorrelated. So for the uncorrelated random variables, this one will be there. Or for the independent random variables, we can say it here. So independence also the same concept will apply here. Yeah. So for the independent random variables, so fxy of x comma y is equal to fx of x into fy of y will get here. Okay. So this one let us take here. I'm going to apply that concept here. Just I'm going to compare that one. Okay. So what we have done is, what we have is, so we have fx y of x comma y is there. So this value is equal to the, you can see now, fxy of x comma y is there. This value is equal to the, okay, so this value is equal to the 1 is there from 0 to 1, and the product of this one is equal to 1 from 0 to 1 here. Okay, so this is comma, not 1. So you can say that since the product, that is fxy of x comma y, so this is equal to the product of this one here, fy of y. We can say the random variables x and y. So if you compare this one with this one, okay, so you can say that the random variable, therefore the random variables x and y are independent random variables here, are independent, or you can say it's uncorrelated. We can say when you're finding the covariance here, sorry, when you're finding the correlation, we can say it's a independent, we can say it here. Sorry, when you are finding the PDF here, we can say it's an independent random variable. When we are finding the covariance, we can say they are uncorrelated, we can say it here. Okay, so random variables x and y are independent random variables here. Okay, so where you're going to make use of this concept is, okay, so as I told, in case of the FSK, that is frequency shift keying, like similar to the frequency modulation, frequency shift keying. So there, when you are going to receive the two symbols 1 and 0, so there, in order to find out the probability of error, we are going to make use of this concept. You are going to make use there here. Okay, so done. So now let us find out the mean of this one here. So you can take the mean of random variable x is given by the mean of random variable x is, so it is nu x. So we know the formula for the mean here. So it is obtained by integrating us. Since it's a continuous random variable, we are going to integrate this one with respect to the dx here. So we know x is the random variable. So we know fx of x, it is defined only between the 0 and 1 here. Fx of x is defined between 0 to 1 here. So I'm going to change the limits of that one from 0 to 1 here. So 0 to 1, x into the value of fx of x is 1 year within this interval into dx. So the integration has become x squared divided by 2. The limit is 0 to 1 will get here. Okay, so it is 0 to 1 will get here. So the mean nu x is equal to, so it is 1 by 2 will get here, 1 by 2. Okay, so similarly, let us find out the mean of random variable y. Mean of random variable y. So this is also will get the same value. So nu y is the thing, but let us take the generalized formula. So y into fy of y into dy. So this is 0 to 1. So y into, okay, the value of fy of y is, it is 1 year into dy. So this has become y square by 2. So from 0 to 1. So you can say nu y is equal to 1 by 2 will get here. 1 by 2 will get. So this is the mean of the random variable x and y. Done. Now let us find out the correlation between the random variable x and y here. Let us find out here. So then the correlation, next you can take here the correlation of the random variable x and y. correlation of random variable x and y is given by, so the correlation is nothing but it's the expected value of the x and y. So this is the thing, but I'll write the generalized formula. So integral from minus infinity to the plus infinity. One is for the random variable x, another is for the random variable y, and we have the two random variables x and y, and the bivariate PDF fx comma fxy of x comma y into dx into dy here, into dx into dy. Okay, so since we know that fxy of x comma y it is equal to fx into fy here. Okay, so we can integrate this one separately here. So for the x here, so you're going to get 0 to 1 x into fx of x, we can write here fx of x into, okay, so I'm going to separate here. I'm going to write the generalized first here into dx. So similarly from minus infinity to plus infinity, y into fy of y into dy. So we can do right here, or straight away we can write this expression. So 0 to 1 x into dx plus 0 to 1 y into dy. So not plus, so it's a into here, it's a product here. So that is it's a correlation between the random variable x and y. So this is the integration of x is the thing, but it's a x squared by 2. The limit is from 0 to 1, and integration of y is the thing, but so it's a y squared by 2. The limit is from 0 to 1. So if you apply this one, so this has become 1 by 2 into 1 by 2. So this will become 1 by 4 here. So the expectation, the correlation of the random variable x and y, this is equal to the 1 by 4 we'll get here. 1 by 4. Done, right? Then similarly we have the covariance is there here. Okay, so covariance is there. You can take the covariance of random variable x and y. Covariance of x and y is, so the covariance of the random variable x and y is given by, so covariance of x and y is nothing but it's the expectation of x comma x here, that is the correlation minus the product of the mean here. So nu x into nu y. Okay, so this expectation of x comma y is nothing but we got already, that's a correlation minus the mean of this one is 1 by 2 into the mean of this one is 1 by 2. Okay, so this will become equal to 0. So the covariance is equal to 0 means we can say that the random variable x and y are said to be uncorrelated, we can say it here. So you're going to use the concept of uncorrelated for finding the covariance here. For the PDFs, you're going to say it's an independent random variables, you're going to say it here. Okay, you can say that. Therefore, the random variable x and y, the random variables x and y are uncorrelated. Uncorrelated here. So this is a uncorrelated random variable x and y. And also we can see one more, we can observe one more thing here. That is the expect for the uncorrelated random variables already in the theory classes we have seen. So it is the correlation between x and